So we're told that a 0.280 kilogram croquet ball makes an elastic head-on collision with a second ball initially at rest. The second ball moves off with half the original speed of the first ball, and therefore let's figure out two things. One, or if you like, part A, what is the mass of the second ball? And part B, what is the fraction of the original kinetic energy that gets transferred to the second ball? All right, so let's first of all draw a nice pretty picture. We have ball number 1, which has a mass of m1, traveling at some speed v1. And it hits ball 2, which is originally at rest. So that's the before picture. So that's before. And then later on, m1 is still moving, although it may not be obvious which direction it should be going. Let's go ahead and draw it like this. And if we needed to figure out which direction it was going, we can write it like this. And if v1 prime turned out to be negative, then we would know it was going the other way. So for now, we'll just assume that this is true and see what happens. v2 prime is, of course, going off in this direction. And they tell us right away that v2 prime is actually equal to 1/2 of the original speed of ball number 1. And this is our after picture. Okay, so let's see. What do we want? Let's see. We want to figure out in part A what was the mass of the second ball. So we'll see if we can figure that out. And we're talking about kinetic energy. Let's just label some things. M1, this is 0.280 kilograms. And that's it. Okay, so let's see how much progress we can make. Conceptually, we have a collision. So when we have collisions, that almost always means that we're going to use conservation of momentum. Now, there's something else here that there's a special word in this problem that says that the croquet ball makes an elastic head-on collision. The word elastic means conservation of energy. So in addition to conservation of momentum, we'll also use conservation of energy. Okay. All right, so part A is to figure out what is M2, given these facts. So let's go ahead and do that. In fact, let's go ahead and write down the equations we need. The conservation of momentum, we have the definition for momentum, 1/2 m times v, the vector. Conservation of momentum simply tells us that the total initial momentum is equal to the total final momentum. We'll have energy to deal with. The only kind of energy we have to worry about here is kinetic. The kinetic energy of any object is given by 1/2 the mass's object and the speed squared. There's no potential to worry about. Even if there was, it's all at the same height, so there's no, for example, gravitational potential to worry about because it's not going to change. So that's the kinetic energy, and the total energy, which is the sum of the kinetic energies of both balls, whatever that is, it's equal to the same value later on. So if you like, these are the two conservation laws that we'll need. Okay, let's separate the picture. Using conservation of momentum, we have the initial momentum of, let's just write this with algebra, m1 v1, because there's no momentum from the second object. Later on, we have an m1 v1 prime, and we have an m2 times v2 prime, but that's just equal to 1/2 of v1. Okay, that's the statement of conservation of momentum. Conservation of energy says the initial kinetic energy, 1/2 m1 v1 squared. Again, there's no momentum or energy from the second object there. And later on, it's got a kinetic energy of m1 v1 prime squared plus the kinetic energy of the second ball, 1/2 m2 v2 prime quantity squared. I'm going to go ahead and put parentheses here in case you forget to square the 1/2. That's an easy mistake to make. 1/2 v1 quantity squared. Okay? So we'll use these, and we want to solve for m2. In fact, we're going to want to solve this for m2 in terms of m1. Let's do this completely algebraically for now. If we use the conservation of momentum equation to solve for V1 prime, we can then put that into the conservation of energy equation, and that'll give us an equation entirely in terms of V1. So this is really an exercise in algebra. Hopefully you find this useful. So let's label this one 1 and this one 2. Using equation 1, we can solve for V1 prime. Let's see how this goes. Let's take this to the other side and then divide by m1. In other words, m1 v1 minus m2 v1 over 2, and then divide this whole thing by m1. This is equal to v1 prime. It may be worth cleaning this up just slightly. Notice that you see there's a v1 in both of these terms, so let's just do that. In fact, let's pull that out and write this as 1 minus m2 over 2m1 times v1. So that's one way to rewrite v1 prime. Now that we have that, we can put it into the second equation and make some progress. So let's go ahead and do that. 1/2 m v1 squared equal to 1/2 m v1 prime squared is this thing squared. So what we have is the 1 minus m2 over 2m1 quantity squared v1 squared. That takes care of this term. And then finally we have this over here, which I'm going to go ahead and remind you that 1/2 quantity squared is 1/4 times this 1/2 makes that all 1/8 m2 v1 squared. Okay. The nice thing about this is that the v1s squares cancel, and we can now rearrange this and solve for m2, the thing that we want, in terms of m1. I will skip the detailed steps at this point and just tell you that what you'll find is that 3m1 is equal to m2. And so when you actually plug in the fact that m1 is that value, you'll find that m2 must be equal to 0.84 kilograms. Okay, so we've just done part A. As a reminder, we found that the mass of the second croquet ball must be 3 times the mass of the initial impacting croquet ball, and so that comes out to be 0.84 kilograms. In part B, what we're tasked with doing is figuring out what fraction of the original kinetic energy gets transferred to the second ball. Well, the amount that gets transferred is equal to the final kinetic energy of the second ball, because it started with none. So what that means is the fraction that's transferred, let's just write this in words. Fraction transferred, I have to spell this right, is equal to the kinetic energy acquired, so that's 1/2 m2 v2 prime squared, divided by the original kinetic energy that the first ball had. In other words, 1/2 m1 v1 squared. Okay. So now all we need to do to, I feel like this is f, this is the number that we're trying to find. The two simplifications to make, or the things to include now, is that m2 is actually 3 times m1, and v2 prime itself is 1/2 of v1. Remember to square that. That's why I add these parentheses, just because I want to make sure I don't get too confused, and divide this by 1/2 m1 v1 squared. The m1s will cancel, the v1s will cancel as well, and this turns out to be 3/4. The 1/2s cancel, the 3 gets multiplied, 1/2 quantity squared, which is 3/4, and that is your final answer.